Hello everyone. In this session, let's try to understand another most powerful machine learning algorithm called as support vector machine. So just like neural networks, you find that support vector machines are also very complex to understand. So the mathematical models behind the support vector machines are also very complicated. But at the same time, because of the various technologies like R, which have already built in the various attributes associated with support vector machine, as a business user, I can very well use those support vector machines for doing my prediction purposes. So I can train my model, I can train the machine with this support vector machines algorithm on the training data, and based on whatever the learning that the machine has been able to do, I can use that learning to do the prediction on the testing data before I roll it out to the production world. So as a part of this session, just like in neural networks, I won't be getting into the detailed mathematics associated with the support vector machines, but some basic terminologies, some basic conceptual aspects that are associated with the SVMs, I'm going to cover them. So initially we'll talk about what are support vector machines, how do you differentiate between support vector machines and the various other machine learning algorithms we have seen till date. So here we use a terminology called hyperplane. So how is this classification of the data occurring with the help of hyperplanes? Right, I can use this both for classification purposes as well as for numerical prediction purpose. So we can see how is this grouping occurring with respect to hyperplane. So how do I really identify what is hyperplane first of all, and how do I really identify the maximum margin hyperplane for the data which is linearly separable, or in case of non-linearly separable kind of a data? How do I differentiate in terms of finding out the hyperplane? And then we are looking at what do we really mean by kernels. In case of support vector machines, we talk about kernels especially for non-linear spaces. So if the data is, if the relationships between the variables are non-linear, we talk about converting them into linear using what are called as kernels. So let's try to understand what those kernels are all about. And then we talk about different types of kernel functions that are there, specifying what are the goodness, what are the advantages and disadvantages that are associated with support vector machines. So once we have a good understanding of the basic theoretical aspect behind the support vector machines, we can very well continue the same prediction example that we have done, and we can go ahead in terms of predicting with the help of support vector machines, and finally do the goodness of fit of the model by finding out the R squared on the test data. So conceptually, when we are talking about support vector machines, we are clearly defining a surface. We are defining a surface. So we are talking about different points. So let's say these are some set of points, these are some set of points. We are defining a boundary between various set of points. Different ways in which I can define the boundary. I am defining a boundary between various points of data according to the feature value. So we are having the various data plotted, and I am trying to segregate the different kinds of data by drawing boundaries across the various elements. So the major goal of support vector machine is create a kind of a flat boundary. So the flat boundary could be a two-dimensional boundary, which is simply a line, or it could be a three-dimensional boundary or n-dimensional boundary, which is a plane. So that kind of a boundary that we are drawing or creating is called as a hyperplane. So the intention is whatever the partitioning that is happening on the data, so the values are more or less uniform on either side of the partition. This is more and more we are talking about the categorical data. Of course, the same thing will be applicable even for numerical data also, but when we are splitting or when we are drawing the boundaries, we want that those values that are falling within the boundary, they need to be more or less homogeneous, whereas the others which are falling on the other side of the boundary, they should be very much away from this set of values. So there is some kind of a combination of KNN algorithm, which is primarily for the classification purpose, and also a regression algorithm, which is primarily for numerical prediction purpose. So even if the relationships are very complex, even if I have to do a classification or if I have to do a numerical prediction, for any kind of aspects, I can very well use the support vector machine. So there are so many softwares. See, theoretically, understanding them could be very complex, but because of the presence of various softwares, because of the different implementation of the various techniques in various software libraries like R, even though the math is difficult, I can very well understand the whole process. I can use them for the prediction or for creating a model with the training data, evaluate the goodness of fit of the model, and if the model deemed to be more appropriate, I can very well validate the model on the testing data, and if the accuracy of the model looks much better, I can very well roll it out even onto the production data as well. So that's where the SVMs can quite comfortably be used, even if my objective for any kind of a supervisory learning process, even if my objective is classification of the data or even a numerical prediction, in both the cases I can very well use support vector machines just like the way I have used neural networks as well. But when we are talking about binary classification, probably I get the best out of the support vector machines, where I am able to divide that whole data into two groups. So the kind of a plane that I am using for dividing the data, so the understanding will become more and more comfortable when we are using the objective of binary classification. Now, this is how the binary classification typically works, right? It's a kind of a line that I am drawing between the variables, or if I have multiple features, instead of a line, I am drawing a plane. So SVM is actually using a linear boundary. It could be in a two-dimensional, if it is a line, and the multi-dimensional, it's a plane. So in general, we are calling it as a hyperplane. So to partition the data into groups, so if it is a plane, if it is multi-dimensional, then we look at it as a plane. Otherwise, it's a simple line that is doing the bifurcation between the groups. So they are all linearly separable. So I can very well separate the groups with a linear line or a simple plane. But I can very well extend this mechanism even if the groups are not linearly separable. Even if they are non-linearly separable, we say we introduce a scenario called kernels. So because of this kernels, even if the data is not linearly separable, we can use an appropriate kernel to transform the data such that it becomes linearly separable, and we can very well go ahead with the model building process. Coming to the SVM algorithm, the main objective is I should be able to, when I am executing an SVM algorithm, it means that my objective is to identify this particular line or this particular plane that is separating the two classes, that is separating the different groups of data. So I have to identify either a line or a plane that is separating the different groups of data, and the kind of algorithm that we are choosing is always based on a concept of maximum margin. That is the kind of concept that we are using for doing the separation between the groups, the maximum margin mechanism. Now, how do I really find this maximum margin? What is that particular plane that is having the maximum margin? How do I really find that out? The intention of identifying the maximum margin plane is that particular line or a plane which will separate the two groups of data. So the greatest separation between the two groups of data, and which should be applicable for the futuristic predictions as well. So if there are slight variations in the position of points, now here you see if this point comes this side, this point comes this side, that might to what extent the slight variation in the position of the points near the boundary might cause one of them to fall over the line by chance. So it is possible that this can come onto the line, this can come onto the line. So what is that, to what extent I can bring out that kind of a greatest separation between the two classes? And this is where this is called as a maximum margin, this much. So this is what I am calling as a maximum margin, because I am drawing one line out here which is the border. I am drawing another line out here which is the border. These borders are typically called as support vectors. Between the two groups I am identifying support vectors, point from each class that are the closest to the maximum margin hyperplane. So this is what is my maximum margin hyperplane. I am identifying the classes from both the groups which are very close to the maximum margin hyperplane. So they are called as support vectors. So support vectors are a very compact way to store a classification model, even if the number of features are extremely large. So this is the major objective behind the usage of support vector machines. So when my data is very much linearly separable, you see the different points. So we are talking about the maximum margin hyperplane. If I have to really look at the maximum margin hyperplane, first you construct the boundary, outer boundary for all the groups of the data points. These outer boundaries are typically called as convex hulls. And once you have created them, you create a perpendicular bisector of the shortest line between the two convex hulls. Here this is the shortest line between the two convex hulls. For this line you come out with a perpendicular bisector. That is what you will call as the maximum margin hyperplane. So here we see that the sophisticated computer algorithms, they use a mechanism called quadratic optimization, and using this quadratic optimization they are quite comfortable in terms of identifying the maximum margin hyperplane. So that is the major thing that we are talking of. You first draw a convex hull for all the points, which is the outer boundaries of both the groups. Look at which is the shortest distance between the two convex hulls and draw a line, and then take the perpendicular bisector of the same. That is what we are calling as the maximum margin hyperplane. But if my data is not linearly separable, then one alternative is you introduce a slack variable. So slack variable is nothing but this kind of an error variable. So it is creating a soft margin so that some points are falling on the other side of the margin. So here I see a circle which is falling on the other side. Here I see a square that is falling on the other side of the margin. So here I am not looking at the maximum margin. So we are looking at minimizing the total cost. Instead of looking at finding the maximum margin, we are trying to look at the minimizing the total cost. The cost is the cost of misclassification. So I am not looking at maximizing the margin. I am trying to look at the minimization of the total cost. Total cost is the cost of misclassification into a different group. So again, these are there as a part of the SVM packages itself, which is more, when I am talking about the cost, we are talking about a penalty for those examples that are falling on the wrong side. So if the cost parameter is much higher, we are saying that there could be a possibility of 100% separation, because it wants to reduce the cost to whatever extent possible. So there is a good possibility that 100% optimization can very well be accomplished. So this is how the typical non-linearly separable data can be handled, but much more comfortable way of handling a non-linear data is the usage of kernels. We have already talked about we can use a slack variable, and some examples will be misclassified. So there is a cost associated with the misclassification, and I want to minimize the cost that is associated with the misclassification. But otherwise, the most common way of dealing with non-linear spaces is using a kernel trick. So what typically happens in a kernel trick is the problem is typically mapped into a higher dimension space. So there is some kind of a change in dimension that is happening to a particular problem. So by doing some kind of a transformation, the non-linear relationship, now here you could see that all the red ones are following somewhat in a case in the shape of a circle, which is a non-linear relationship. But by doing some kind of transformation, some kind of kernel trick, I could see that they are quite comfortably separable out here. So a non-linear relationship can get converted into a linear relationship by applying different kinds of kernel tricks on the data. So we are looking at the data from a completely new dimension, so that the overall separation between the data can be done quite comfortably. So some kind of mathematical relationships can be looked at, some kind of mathematical transformations are being performed, so that the non-linear stuff is automatically getting converted into linear between the various measured characteristics. So a new dimension we are looking at, and different kinds of kernels are there, so that we can do the classification more and more comfortably. So different SVM algorithms, they support different kinds of classifiers, different kinds of kernels, so that the overall classification can be done quite comfortably. The overall prediction can be done quite effectively. So looking at the strengths and weaknesses of SVM, as I have already talked about in the beginning, SVM can be used for classification purpose or even for the numerical prediction kind of problem. So it is used for all kinds of supervisory learning. That's one major advantage that we can get. Even if we have too much of random variation in the data, still I can very well use the support vector machine. So overfitting is not that heavily possible with the support vector machine kind of a mechanism. So I can use them just like the way I have used neural networks. There are different kinds of algorithms that are supported by SVMs. So I can very well use those SVMs as a kind of a black box, just like the way I have used the neural networks. And there's a lot of popularity that is coming out with this support vector machines, especially for binary classification kind of a problems. But we can very well see for the numerical prediction kind of a problems to what extent we are able to achieve the goodness of it using the support vector machine. Now, here, when I'm talking about the best of the best models, I have to try different kinds of kernels, because there is no mathematical scenario which says this model is the best, this kernel is the best. The parameters I have to keep varying. So whatever are the different kinds of parameters that I have to change, there are different parameters that I have to change. Even I have to experiment with different kinds of kernel functions which are converting a nonlinear to a linear kind of a behavior. So I would have to experiment different kinds of combinations of the kernels and model parameters, and then do a testing on the test data before I can conclude that this particular model is the best model for this kind of a data. So the training process is very slow, and that too if there are good number of features, variables are too large in number, examples are too many. In that case, probably the model becomes much slower. And another problem which is more or less similar to that of neural networks, it's also a kind of a complex black box. The interpretation of the model is quite difficult. So these are some of the things that are existing as the weaknesses associated with the support vector machine. But even in spite of all these weaknesses, still they are quite heavily used, because wherever I don't need to spend too much of time in the interpretation part, but focus more on the predictability, I can very well look at the usage of support vector machines itself. So looking at the very common kind of kernel functions that are used, the general form of a kernel is getting transferred using this kind of application. If I'm talking of xi, xj, so xi is getting transformed into xj by going ahead in terms of some function of xi mapping it to some other function of xj. So mapping of data in one space to a data in another space. Very commonly I can have a linear kernel, which is the dot product of the features. So there is no transformation of the data that is happening here. But I can have a polynomial kernel with a degree d. So we are simply doing a non-linear transformation of the data. If you see here, there is a dot product xi xj plus 1 to the power d. So this is what we call as a polynomial kernel of degree d. So I can apply a polynomial kernel where the inputs get transformed in this particular manner, or I can have a sigmoid kernel more or less similar to that of a neural network. In sigmoid we talked about 1 by 1 plus e to the power of minus x. So that's the similar kind of kernel function that can be applied, where I am transforming the input into a different form, so the non-linearity can very well be transformed into linear. Then I can think of Gaussian RBF kernel, which is more or less similar to an RBF neural network, where the function that we are using is a Gaussian function, which is more similar to e to the power of minus xi bar minus xj bar whole squared by 2 sigma squared. Right, a sigmoid function comes out with tan h, which is the hyperbolic tangent kind of situation. Tan h of k times xi bar dot xj bar minus delta. So we are applying different kinds of kernel functions where a non-linear relationship can very well be transformed into a linear relationship, and the classification or the prediction of the values become more and more comfortable. But the worrying part is there is no single rule which says this particular kernel transformation is more and more appropriate for this kind of a data, for this kind of a learning. So I have to try all possible kernel combinations, and based on that I have to see where the prediction is coming out more and more appropriate. So what kernel function that I have to use is purely based on what should be the learning, how much of training data is there for the learning purpose, what is the level of relationship, is it a linear relationship or a non-linear relationship between the various variables. All these things will really drive what should be the type of kernel function that I have to use for my kind of data. So the common method typically for identifying what should be the kernel function is we are training, evaluating different kinds of SVMs, and whatever the models that are getting built, all of them we are again testing on a testing data set, and whichever one is fitting more and more appropriately, that is the one we are concluding. So that is how we will work on our example right now. So we'll take the same data set that we have used, right? The one that we have gone ahead in terms of building the neural network as well. So we'll use a similar data set, same data set for building our SVM as well. So SVM learners require all features to be numeric. We have already taken care of that even when we have built the neural networks. So normalize or standardize the data, even that we have done. So I'll consider the insurance 1 underscore Z, because that is the one where I have already normalized, or I can directly use my train data and test data because they are already based on that normalized itself. So in some cases, some SVM packages do it automatically, this normalizing and standardizing. Otherwise, I may have to go ahead into doing that particular process. So I have already split the data into training data and testing data. Now we will go ahead in terms of training the model. There are so many implementations, but so which means I can use either E1071 package or KLR package, Kernel package. There are different kinds of packages that I can use. So I will go ahead using the Kernel package, right? So I can use different kinds of automated methods and all which are there as a part of the package. So let me use Kernel as a package. So I'll use Kernel as a package. Kernel. Okay, I'm installing the Kernel package. All right. All right. So we are going ahead with the Kernel package. So I have already installed. So let me load this Kernel package. Though you can use any other packages as well. So within this, I am using this function called KSVM, wherein I have to give the target, then the predictors. Here I can very well give the dot notation. So I have to give my dependent variable, I have to get the list of my predictors, the data function I have to, the data from where I'm building the model. I have to give my kernel, what are the different kinds of kernels that I can use. So here generally I'll go through the help function, but otherwise I can give RBF dot, which is the radial basis kernel, or I can give poly dot, right, as I have given radial basis. If I want, I'll give RBF dot. If I want a polynomial kernel, I have to give poly dot. If I want a sigmoid kind of a kernel, hyperbolic tangent, I have to give tan h dot. And if I want a linear kernel, then I can give vanilla dot. So I can very well specify what kernel do I really require. And I can also give the cost parameter, especially if the constraints are getting violated. So how big a penalty is there for that kind of a violation. So if it is very large, the margins will be very narrow, and vice versa. So I can very well create a model like this. So let's talk about model underscore SVM, where I'm talking about KSVM as a function. right? Charges are my dependent variable, dot is my independent variable, the data is train data in this case. I've already done the I've already done the normalization. We use the scale function to do the normalization of the data. So I'm giving that as my train data. So kernel by default is RBF dot. So let me use that RBF dot itself. After that, let me change the name of the kernel. And right now I can just set the C value. If I want, I can set the C value, otherwise I really don't need. Or in some cases, if I just want to start with the base, I'll call it as a linear dot, or sorry, vanilla dot for linear kernel. So I'll set it as vanilla dot. I'll show you all the various possibilities that you can give. So I'm training my model this way. So all the other kernel parameters are set as default. So your model got typically built. Now let's try out first of all KSVM. What are all the things that it is offering for us? It has a wide variety of things for us. You could see here KSVM, right, for formula. So we are talking about X, which is a formula, right? When we are talking about a formula, we are giving X. We are talking about the data for this, and we are also talking about the kernel, which is RBF dot. But if you see here, okay, the type KSVM can be used for classification, right? Okay, here we'll see a few more things. X is a symbolic description of the model to be fit. When not using a formula, X can be a matrix or a vector containing the training data or a kernel matrix. But when I am using it as a formula, I can very well give that tilde sign. Then I am giving my data. So the training data from which the KSVM function is typically built. But otherwise, I am looking at scaled. A logical vector indicating the variable to be scaled. If scaled is of length 1, the value is recycled as many times as needed and all non-binary variables are scaled. So if at all, if we are setting the scaled equal to true, then the scaling is typically getting performed automatically. Even if we have not done the scaling, it will take care of doing the scaling for us. Then the other important parameter we should look at is type. Right now it has gone as a default. But you could see KSVM is used for classification, regression, and even for pattern identification, novelty detection. So depending on whether Y is a factor or not, the default type is CSVC or EPS SVR. So when you say CSVC, it's a classification kind of stuff, right? But EPS SVR, it's actually a regression model. So now actually I require it as a regression model. So I need to set the type as EPS SVR rather than CSVC as a type. If we are seeing here, we did not specify the type, but we have to set it as EPS SVR so that we can get it as a regression model. So let me improvise this, right? Otherwise the default is CSVC. So let me set it as type is EPS SVR, right? So that's one more thing we are getting. We need a regression. Can be used for classification or regression or novelty detection. So for the regression, we are seeing that we will set it as EPS SVR. So these are the different kinds of options that are there. Similarly, you see kernel functions. There are so many kernel functions that are used for training and predicting. Right? You could see RBF dot radial basis kernel, which is more like a Gaussian. poly dot for polynomial kernel, vanilla dot for linear kernel, tanh dot for hyperbolic tangent kernel, Laplacian kernel, Bessel kernel, ANOVA RBF kernel, spline kernel, string kernel. So there are so many kinds of kernels that are typically supported. And there are different kinds of parameters also that it supports. So that means you have quite a lot of options that are there when we are building the model using the KSVM. So let me try building the KSVM model. We got model underscore SVM, right? Now if I am typing the name of the model underscore SVM, you could see it's a support vector machine of the object KSVM. The type of the support vector that we are using is it's a regression model. So there is a default epsilon value that is set. Cost value is also set to be default. So there are 382 support vectors that are created. The training error is around 0.3188. So that is how the model got created for us. So you could very well look at the summary of that model as well. So here the model is saying that the mode of it is S4 kind of a mode. It's a class KSVM. So we will try to do the evaluation by doing the prediction on the test data. So I can very well say P underscore SVM, wherein I am doing a predict. The model is model underscore SVM and I am testing it on the test data. Right, in the test data, so we are executing this model on the test data. The vector does not match the model, so it's better that I take test data, I remove the input out of it. So I'll take all the rows, the output variable I'll remove. So fifth column I would remove from it. So that's how my model got built. So PSVM, we got it as the model out here, right? We have predicted based on the PSVM model that we have generated. We have done the prediction part. Now I can very well go ahead in terms of using this particular prediction, finding out the correlation square, which is the R square. So I'll take the correlation between PSVM as well as test data dollar charges. I take the square. Okay, so better instead of saying test data dollar charges, I will take test data all the rows and the fifth column. Let me take the square of that. So this is resulting in only 76.31%. So going with the linear kernel, my model is giving me only a 76.31% accuracy. Whereas let me try some other kind of a model out here, right? The linear is giving me 76% accuracy when I'm going with vanilla dot. But let's say I'm going with a poly dot. Instead of vanilla dot, I'm doing this with a poly dot. All else remaining the same. Now in this case, if I'm talking about the model SVM, so here the training more or less looks like the error is more or less similar, right? If I want, I can do the prediction of the model, right? I have to do the prediction based on this. So the prediction is done. Then I am trying to do the R squared using this poly dot. Even this one is giving me 76.31 itself. So whether I am going with a vanilla dot or a poly dot, my result looks more or less similar. But what about if I am using an RBF dot, which is I am going with a radial basis, right? So that's how I can very well go ahead in terms of experimentation. Okay, I'm going with RBF dot. Now if I'm checking the model, I'm not sure whether I can, oh, the error got down quite drastically. You see here, all these cases the error was 0.31, but here it came down to 0.15, almost half of it. Right, so there's a hyperparameter sigma value, it has typically checked because the RBF function again goes with a particular formula for the transformation. There are 372 support vectors and the objective function came to this particular value. But whatever it is, now I can do the prediction using this particular model on the same test data, and once I have done the prediction, I can very well find out the correlation squared, R squared coming out to 86.54. So that's how I can go ahead in terms of seeing whether this model is more and more fitting my test data or not. So if I have to compare it, probably the neural networks have gone to the extent of 89%, but of course here also I can very well change the cost. So let me see now, if I am introducing the cost a little bit, let me see if the model is improving by any extent. So I am setting my C value to 2 instead of 1, all else remaining the same. So when I test the model now, the error looks slightly lesser. So I am hoping that the accuracy should be slightly improved because of this new error function that I have brought in. So it looks like 86.96. Earlier it was 86.54. So probably let me work it out with even more increasing the error function. That's how we play around. Right, I am setting a very high error value. And now let me see if my model has improved any more further. Yes, training error came down to 13.8. But let me try to test it on the testing data as well. And now I could see the error 86.87, whereas in the earlier case I was able to touch 86.96. So I may be drawing a line somewhere, seeing where exactly things are improving. So I have to try different kinds of kernels, I have to try different kinds of costs, and finally change all other parameters whichever are there in my scope. Finally test them out on the testing data to finally come out with which model is more and more appropriate to this particular data set, so that I can use based on the accuracy, I can very well go ahead in terms of using this model for the production world in the real world. So I'm comparing the predicted with the actuals, looking at the accuracy of the model. So instead of linear kernel, I can use different kinds of complex kernel functions. So wherein the data is getting mapped into a higher dimensional space so that a perfect fit can come out at a later point. Or I can play around with the cost constraint parameter so that appropriate bifurcations of the data is happening comfortably. If I look at the plot of the model, right, if I am looking at the plot of this particular model, so here the plots are typically not coming up. Only for classification purpose I can generate the plot if I am using the classification part, not for the regression part. In that case I can very well generate the plot, but here because I am doing a regression using the support vector machines, I can't get any kind of a plot directly using this particular function, right? So this is how I wanted to look at support vector machines, compare them with the various other types of machine learning algorithms. So get a basic idea, though we are not getting into a high-end mathematics using the support vector machine, we can very well get a comfort layer in terms of how to use them for doing the regular classification and numerical prediction tasks. I hope you got a fair amount of idea in the usage of support vector machines for both classification as well as numerical prediction purpose. If you have any further queries regarding the same, you can get back to me by giving me a call on the number that I have provided below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.